So, hello and welcome to our next lecture. We will continue with the topic of bootstrapping and go a little bit into detail about error estimation, bias estimation, and also about the related methodology of the jackknife. So, as a quick reminder, we were talking last time about bootstrap sampling. For example, the non-parametric approach is presented here. Again, briefly, we wish to identify a certain parameter of interest or several parameters of interest. We compute those for a given data set and then regenerate artificial data sets of length n by resampling with replacement from the ECDF of this data set, which is the non-parametric approach. If we were doing the parametric version of bootstrapping in this position here, we would sample from the parametric distribution with the parameters of interest filled in from its previous estimate denoted above. Given those bootstrap samples, we can compute the bootstrap estimates of our parameters of interest and thus gain a whole lot of samples of the actual parameter of interest and therefore an estimate of its distribution. Related to the bootstrapping method is the jackknife method. It was originally developed by Ken Wee, and Tukey, who is famous statistician of 20th century, was the one who expanded this method and also proposed its name as the jackknife. For those of you not familiar with this vocabulary, this is jackknife. The argument of Tukey was this is a rough and ready tool that can improvise a solution for a variety of problems, even though specific problems may be more efficiently solved with a purpose-designed tool. This applies to the jackknife and also to its generalization, the bootstrap, and therefore I wanted you to have this quote. The idea of the jackknife is that we resample basically in the leave one out methodology. So we generate our samples based on the original data by just leaving out one of the observation each time. In this way, it's pre-specified how many of these jackknife samples we will actually gain. And also with the parameter estimates, which we are gaining from these jackknife samples, we get an impression of the change which is induced by leaving out a single point of our data set. So note that there are different sample sizes for the original estimator and each of the jackknife estimators, of course, since we're leaving out one observation each time. Jackknife nowadays is often used in combination with bootstrapping, and we will take a look at why this is the case. In order for the jackknife to work nicely, this parameter estimator theta hat should be a smooth estimator in the sense that small changes in the data cause small changes in the estimate. This is, for example, not the case for the median, where changing the data a bit creates no change at all if you're doing it in the tails of the sample data distribution. However, it may create an abrupt change if you do it with the two values in the center. Whereas the mean fulfills this smooth quality that changing a little bit of the data always will change a little bit of the mean. So the jackknife has a standard error estimator, which is basically the square root of n-1 divided by n, the sum of all these jackknife estimators of our parameter of interest minus the mean of all of them squared. This factor n-1 divided by n is needed to make this estimator here unbiased. I'm specifically, it's specifically relevant that these jackknife estimators are unbiased, because this is a quality which makes them useful for estimating bias of other estimators. So the unbiasedness of the jackknife mean is basically given by this formula here. The sample mean is identical to the jackknife mean, which is the mean over all means of all jackknife samples. We can see this directly here, because each of the jackknife samples only has n-1 observations. Each of these means is calculated by 1 over n-1, and in each of these sums the specific value xi appears n-1 times, and therefore this cancels out, and finally we arrive with the original sample mean. Also, it holds true that the jackknife standard error, as we saw it defined above, this n-1 over n, sum of the means minus of the jackknife samples minus the total mean squared. This is basically 1 over n times n-1, the sum of all observations. Each of the observations comes in n-1 times, minus the sample mean squared. And this is basically the standard error, which is the sample standard deviation divided by the square root of the number of observations. So in this sense, the jackknife estimator is unbiased. The jackknife mean is always identical to the sample mean. The jackknife standard error is identical to the sample standard error. To look at this computationally, we do a very quick computation of the mean of the standard error, which we would expect originally from this data, which is 1 over the square root of n. The specific sample error which we have, or the specific standard error which we have for this particular data set which we sampled, we're of sample size 50, and we compare the jackknife means, calculating the means, leaving out each observation once, and then calculate this jackknife standard error as we did above. And we see that the mean of those jackknife means is identical to the original sample mean. We also see that the standard error is identical to the sample standard error. So how do we use this property? One of the earliest motivations for creating the jackknife algorithm was to actually estimate the bias of an estimator theta hat from the expected value, from the original value theta this is supposed to have. And in order to look at this, we obtain these jackknife samples and obtain the mean of all jackknife samples and compare this jackknife sample mean against the original estimator, doing this for every single step, leaving one out in every single step. We get the biases of every single jackknife estimator from the estimator we're supposed to obtain. n multiply by this n minus 1, as this is what we are otherwise dividing by. In this way, taking the estimator we have, subtracting this bias estimator, we get a bias corrected version of the jackknife estimate. And this is what we are talking about when we have bias correction, also for Bootstrap sample. So jackknife after Bootstrap will be the magical words here. This is very popular to combine the two methods. Applying the jackknife algorithm, of course, becomes very tedious as soon as sample sizes get large. But with the Bootstrap algorithm, we saw that we might already arrive with 1,000 or maybe 10,000 Bootstrap samples somewhere reasonable for an estimate. We do not need millions and even more millions of observations, and therefore for Bootstrap samples and Bootstrap estimates, which themselves are random variables and biased, therefore it makes sense to get an idea how large this actual bias which we are creating through the Bootstrap sampling process is, and how to properly obtain the standard error for these. So we will now look at the Bootstrap samples instead of the original ones, and we look at all the standard errors of every single Bootstrap sample and obtain a pool which is obtained in such a way that we look at the jackknife estimates for each of the Bootstrap samples in every step and compare these over all different Bootstrap samples. Based on these, we can then obtain a bias estimation of the total mean of all our Bootstrap sample estimators. And the bias then is this total mean subtracted by every single value and all these biases added up. And once we have this, we can obtain a bias corrected version of the Bootstrap estimator, which is the bias corrected Bootstrap estimator. Davison and Hinckley were very good at describing these methods, the Bootstrap methods and all their applications, so they're still, in spite of being quite old, a recommendable book in that direction. And we will now look at the actual coding of all this methodology. There is a library for bootstrapping. Surprisingly, it's called Boot. And we will now sample an original sample of size 50 and just take a Bootstrap sample of size 200. And based on this, look at all of our outcomes. So the original sample mean of a random normal sample of 550 is minus 0.063. And now we create a mean function which by definition has a certain bias. So we cannot take the original mean, as this would be unbiased compared to what we're estimating here. So we create the biased mean function by just taking the mean of the i's observation each time. In this way, we create with our Bootstrap sample of size 200 a new mean, the Bootstrap mean, which is basically the mean of randomly drawing just one observation out of these 50 with replacement, and that 200 times. For this approach, our original estimator again is what we saw up there as the mean estimator, and the Bootstrap estimator of this approach has a bias of 0.009, whereas the standard error of 0.13 is very close to the standard error which we would expect in this scenario, which is 1 over square root of 50. So bias is unrelated to the standard error. This is about how far off this original value and the bootstrap value actually are on average. Then there's also a handy function for constructing these bootstrap confidence intervals. The boot mean from above we put in here. This object also contains more than just the mean estimator from before. It also contains all the information about how these bootstrap replicates were produced, and based on this whole bootstrap distribution, we can then obtain the bootstrap confidence intervals. We look at 3 different versions of the confidence intervals in comparison. If you remember, we were talking about 2 of these last time and how you construct them manually. The first one was the bootstrap confidence interval based on the theoretical normal distribution, which is motivated by the central limit theorem kicking in for this bootstrap sampling. Then we were also looking at this percentile confidence interval construction, where we take the lower and the upper percentile of the ECDF of the bootstrap samples, and based on this construct a confidence interval. And finally, in comparison, to give you something new to gain from with this boot CI function, there is the BCA, the bias corrected and accelerated bootstrap confidence interval, which already has, in this bias correction, which we were manually doing here, integrated also into the whole estimation process of the bootstrap confidence interval. As you can see, there are warnings that these two might be unstable, whereas the first one, based on the normal distribution quantiles, will hold quite surely. All of these, as we can see, are pretty close together. You see that the furthest off are these percentile confidence intervals. This is one of its main bad qualities, that it is most driven by the resampling process, and therefore this is the least recommendable one to actually use in practice. Good. So which are scenarios where we might have to adapt our original bootstrapping strategy, which we have used quite well up until now, where we were simulating either from the basic data generating process as we imagine it to be, or from the ECDF of our data? Well, this parametric non-parametric bootstrap approach works even more generally than just for IID data. However, if the data is not necessarily IID, dependent data as in time series, or dependent data as in regression, or simply data for hypothesis testing, where we assume a given data distribution under the null hypothesis. So what do we do then? Well, let's start out with the simplest of all of these, hypothesis testing. Basically, we have some kind of testing problem. We now just look at the two-sided testing problem. You can easily adapt it to any one-sided tests as well. We have the null hypothesis that theta is actually equal to some assumed value theta 0 versus the alternative hypothesis that theta is not equal to this assumed value. Basically, for any hypothesis test, this null hypothesis has some kind of assumption for the data to hold, for the parameter to be a parameter either of the data distribution or in some way related to it. So once we know which null hypothesis we want to test, we can basically simulate from that. So this is the idea of the parametric bootstrap method. We know which the null hypothesis model actually is. We plug in the values we obtained from our original samples, and then we obtain new samples based on this pre-specified null hypothesis model and compute the new test statistics for each of our bootstrapping methods. And once we have all of these test statistics based on the distribution of all test statistics and the test statistic of our original data in comparison, we can obtain the bootstrap p-value for this kind of test, which is the number of all simulated bootstrap sample test statistics, which are more extreme than the original data value, plus 1 divided by the number of bootstrap samples, plus 1. This plus 1 is again for the bias correction, and it also has a stabilizing effect that this will never be exactly 0. So let's look at one of the most famous test scenarios, the student's t-test. Student's t-test is about asking questions regarding the mean, the expected value of normally distributed data when we have some pretty good idea what the variance of this data is, and we assume that this data variance stays the same for all data points and is well enough approximated by the sample variance. So once this holds, approximately normal distribution of our data, then under the null hypothesis, the model is that this is normally distributed around this assumed value mu zero, and the variance which we're assuming for this normal distribution is well enough approximated, of course not by Sn, but by Sn squared. Yeah, whereas the standard deviation is well enough approximated by Sn. The test statistic is the classical t-test statistics, which is the mean of our sample minus the assumed mean under the null hypothesis divided by the sample standard deviation. Again, we obtain all of these similarly constructed bootstrap t-test statistics by just filling up in the mean of each bootstrap sampling and the standard deviation of each bootstrap sample. In this case, we know what the theoretical distribution would be like. It would be the student's t-distribution. However, we obtain our p-value now with the purely parametric bootstrap way, and we count all the times that the bootstrap t-test statistics is more extreme than the original test statistics, plus 1 divided by the number of bootstrap samples, plus 1. The non-parametric case for this, instead of assuming the normal distribution, which is very specific for the student t-test, which is a parametric test in itself, In the non-parametric bootstrapping approach, we only take the ECDF of our data. We only assume this is our knowledge about the distribution of the data. Still, we assume that the null hypothesis holds true, and therefore we simulate from the null hypothesis model. In this case, this is data from the ECDF, which is well enough representing the actual underlying distribution, but we do not assume under the null hypothesis that the mean would be the sample mean. We assume that the mean should be mu0, and therefore we have to recenter our data around mu0 by subtracting the sample mean and adding the value of this mu0, creating a pseudo data set from which with ECDF we're actually simulating the bootstrap samples. Again, once we have constructed this pseudo data set, we create our bootstrap samples, drawing from it randomly, and similarly to the parametric case, we obtain the test statistics for each of them, and also identically as before, the bootstrap p-value as the number of times of observing and more extreme bootstrap test statistics than the original one plus 1 divided by number of bootstrap samples plus 1. So let's look at this specifically for the t-test scenario, which we were talking about above. We simulate data from a normal distribution, 100 of those, and we set our assumed mean mu0 to 2, whereas our simulated data was from a mean of 1.8. The X bar is the mean of our simulated data, which is 1.9. And now here we have the function definition of the t-test statistics. And we construct it in such a way that we fill in this mu0. Basically, this is nothing new. Now we start out comparing the parametric bootstrap for this test. What do? We simulate data from a normal distribution, same number of observations as in the original version, with the mean being this mu0, as we are in the null hypothesis scenario of the t-test, and the standard deviation equal to the standard deviation of the data. And fill all this into this t-test statistics and replicate it 500 times, so we have 500 bootstrap samples. We see the bootstrap estimator for the p-value is 0.315. The actual student's t-test for this example would have a p-value of 0.3129. So we are getting pretty close. The price we pay is also for the bootstrap sample. We have to assume normal distribution scenario. In the non-parametric version, we do not have this assumption of normality. However, here we do the rescaling of the data. We subtract the sample mean, we add the mean under the null hypothesis, and then we sample from this re-centered data as many times as we need for our bootstrap scenario, which is 500 bootstrap samples. Here we obtain a p-value of 0.347, a little bit further away, but in the same order of magnitude. And in this case, we could live without the assumption of normality holding. However, applying the t-test statistics when normality is not holding might not be the brightest of ideas. So what to do if this fails and normality is not holding? Well, originally there are also tests which are based on non-parametric measures for testing the same hypothesis as the t-test. And also there is specific type of resampling methods which are doing something similar, and this is sign tests and permutation tests. And since they are specific versions of the bootstrapping, we will also take a look at those. So we look at the sign test first. We start out with looking at the symmetry of the data around the value assumed under the null hypothesis, which is mu0, and we recenter the data by subtracting this mu0, and now we count basically all the times of values being below this mu0 and values being above this mu0, and this number of positive signs compared to all the observations is basically the test statistics of the sign test. It is nothing else but what we did before in the bootstrapping approach, just to show you that this methodology is basically a resampling based methodology. And then there's permutation testing. Permutation testing is a very nice and elegant version of bootstrapping. So basically we do have a sample. Typically, in order for permutation tests to be quite reasonable, it makes sense to use them for rather small sample scenarios. As you might be aware, the number of permutations is n factorial, and this n factorial, already for n being larger than 200, is basically more than the number of atoms in the universe, and therefore it becomes quite obvious that this will become computationally infeasible to do for large samples. So permutation testing is based on a very simple idea. We have an original sample. We have a few observations belonging in one category A, a few observations belonging in the second category B. We're asking the questions, do all these two categories actually have the same mean? Under the null hypothesis, the two actually have the same mean, because we're asking the question, is the mean different? Therefore, the alternative hypothesis would be, is the mean different? And so under the null hypothesis, basically the coloring of all these observations is irrelevant. We have one mean for everything, which would be the total sample mean, since they are one and the same mean anyways. So based on this idea of having just one mean for everything, and all the observations being from a distribution with the same mean anyways, under the null hypothesis, we just start permuting the labels. The labels are what's encoded in color here. So we just start randomly choosing values from above and saying, okay, this one, this one, this one, this one, they are blue, they are from the first sample. The other ones, they are red, they are from the second sample. And we do this resampling as many times as we have possible permutations for all these labelings, and then obtain the distribution of all possible statistics resulting from this. And look at our original test statistics in comparison for the original data and obtain the p-value as the number of simulated values above this threshold divided by all simulated test statistics. So much for testing. Let's look at something rather different and rather more interesting: linear regression. Linear regression is the backbone of statistical modeling, and therefore knowing how to handle any type of regression model and more generally plugging it into Bootstrap algorithms is quite a useful tool to have. So just as a quick reminder, linear regression is about modeling the actual observations yi as some beta zero intercept plus some coefficient beta I multiplied by the first x coordinate and so on until the p coefficient multiplied with the p x coordinate plus the epsilon i's, the residual errors. This is basically modeling the regression hyperplane, which is defined by this linear equation. There are certain model assumptions for the linear regression model which must hold, and the assumptions A1 to A4 are the ones which we cannot fit the model without. So first one is that this X has to have full rank, which means that all explanatory variables are mutually independent. This one's quite relevant. A famous example of this having to hold true is in medical statistics. Typically, weight might be quite important for predicting heart attacks or whatever, or diabetes or whatever type of diseases. However, if you're larger, you're also supposed to have greater weight, and therefore height and weight of a person is highly correlated. But you need the information about the height in order to interpret the weight. But as they are not mutually independent, but highly correlated, they cannot go into the same model at the same time. And the basic trick for solving this type of problem was to create an artificial variable which has become almost as famous as the original ones, which is the BMI, the body mass index, which is basically the weight divided by the height squared. And its origin is that we have to avoid this assumption. The next one is rather trivial. We want to have no systematic bias, therefore the expected value of the residuals has to be 0. Also, the residuals are supposed to be uncorrelated. This will hold true for IRD data. As soon as we start modeling data which are, for example, time series data or spatially correlated data, we will also see correlation in the residual error unless the model is able to take care of that. And this is the idea behind the construction of a lot of time series models, such as autoregressive models, that these errors have to be uncorrelated. The fourth one is that the residual errors are homoscedastic, which means that the variance must not change for different sizes of the residuals. These four are absolutely necessary. The fifth one is an added bonus. If we already have uncorrelated residuals with expected value 0 and covariance sigma squared times identity, well, we might as well assume that this is the mean and this is the covariance matrix of normally distributed residual errors. So under the assumptions 1 to 4, we have that this is unbiased, and therefore our linear estimator has the same expected value as the original data yi, and also the variance is identical to this estimated variance sigma squared. If we also gain the normal distribution, then we gain normal distribution for the data yi, and therefore gain that this actually is the mean and not just the expected value of the yi's, and we can plug in this variance as the variance of the yi's. This will be important for us here in the parametric bootstrap scenario at first, and it will also be important at a later point when we start looking at Bayesian models and why the Bayesian regression model is assuming just this formula, because it already applies in the original regression model, but we hardly ever write it like this. So how to bootstrap for linear regression scenarios? There are several approaches for this. One is based on the residual errors. We've heard a lot of assumptions are made about the residual errors. They're pretty important. They're basically the deviance of the data points from the linear regression hyperplane. So since we have these residuals and we know in the parametric case that these residuals should have a normal distribution with mean 0 and a constant variance, as we assume homoscedasticity, which is the residual variance which we can estimate from our original data, we might as well simulate a lot of new residuals in each step and obtain bootstrap datasets by adding these residuals to the estimated values on the regression hyperplane, which correspond to the underlying x values for estimating this y hat. Well, once we have this, we can then simulate for these new yi's with the original xi's the model and see how the parameters of the model will vary. The non-parametric solution for this is not assuming normal distribution for the residuals, but assuming that the distribution of the residuals defines itself, and therefore we draw from the ECDF of the distribution of the residuals, and again in the same way obtain the new bootstrap datasets by adding these simulated residuals to the estimated values on the regression of the regression model, and then feeding new models for that. Well, in this way we can then also estimate the bootstrap covariance matrix. If we remember, the covariance matrix in the linear regression scenario is basically the deviance of these betas from the mean of those. It's related as this beta hat contains the original data matrix of the x quite prominently, with related to the original data covariance. Based on the bootstrap estimators, we can therefore estimate the bootstrap covariance without changing the original data xi and obtain an estimate for this. And this is based on the bootstrap estimators and how they are deviating from our original estimate. An alternative way of sampling the residuals and adding the residuals to the theoretical value based on the model which we've already fit is to take the original data points instead and simulate bootstrap samples based on the original data points, simulating with replacement. There are a few pros and cons for both methods. They're said to be asymptotically equivalent when the model is correctly specified. However, we keep in mind the famous quote which was announced for George Box, although it was never verified. All models are wrong, but some are useful. So having a correctly specified model is a dream, but not necessarily something which might come true in reality. So we have to look at what happens in different real-world scenarios. First, they will become quite different once we have small samples, which is not so reassuring. And if we do have small samples and the model is more or less correct, means reasonable, the residual version is more efficient because we have only a few samples available, and this will introduce more variation into the few sample points which we have available. Therefore, it makes it more efficient. On the other hand, the pair strategy is considered more robust if the model is misspecified. So with a correct model, but small sample, residual version works out. With large model, however, we're not so sure if the sample is actually the correct one. The pair strategy becomes more robust and will not be bound so much by the value of the original model estimates. If we had heteroscedastic data, there's also an alternative which is trying to get this heteroscedasticity under control, which is called wide bootstrap, but we will not discuss its details here. Instead, we take a look at one practical example of how to do this bootstrap, the two versions of this bootstrap simulation for actual data, linear regression data. We look at this survival data, which is included in the boot library, and it has the survival times as opposed to some dose of a drug, which are clearly decreasing. And what we can also see clearly already from the scatter plot is that a lot of points are really nicely behaving, like they were along some straight line. However, there's one which is quite outlying with respect to this straight line behavior. So we look at the fitted model for the log survival times, modeled by the dosage of the survival data, and we obtain the original estimators for the original data of the intercept value beta 0 and of the actual slope of the linear regression line for the dosage for the log survival times. Both are strongly significant, so makes sense to fit the model. However, are our assumptions fulfilled? In order to answer these questions, we have the residual diagnostics plot. If you have not seen them yet, we will briefly discuss them. The first one is the residual versus fitted plot, where we see the residual plotted against the fitted value. And we see here that they are centered around 0, which is why the 0 line is put in here as a small grayish dotted line. Yeah, this is more or less fulfilled. However, we see already that something is happening here and this point is really far off. We were expecting to have one point which is far off. We already saw this in our original scatter plot. Scale location plot shows something similar as the residual versus fitted plot. Again, here we do not see that this is centered around 0, as these are the standardized residuals and the square root taken of those. But we see the assumption 2 and 3, which is correlation between the residual errors. And what we can see here is that there is no systematic structure either in the residual or in the standardized residual, which is reassuring. We don't want that anyways, no correlation. And in addition, we want homoscedasticity. There's something happening in this direction here. We see that here the variance is rather large, and then at the end for these higher fitted values they're getting really small. So in this case the variance is changing based on the value, which is not good, but we will see how this is affecting what we're doing later in our simulation. Also, we see in each of these plots that the point number 13 is creating a lot of trouble for us. Checking the fifth assumption, the normality, we see that more or less those points fit well. Well, there's one really deviating from this and one which is a terrible outlier. And this terrible outlier is not just an outlier, it is a leverage point. And the residual versus leverage plot shows us this leverage effect here. And in order to show you what this means visually, this is point number 13, as we could have expected. And the red line is the line which we fitted here for the model. The blue line would be the line fitting all the other points except for this one. And this change of the slope from the blue line to the red line, and the change of how this actual regression line is going through the points, this is the leverage effect of the leverage point. So let's see how this is affecting bootstrapping. We first look at the bootstrap sample of the points. So we simulate from our original data points and then look at the coefficients for those. This is the first thing we plug into the boot function for this survival data, and we look at 1,000 bootstrap estimators. Basically, it assumes this to be non-parametric. We are really not assuming any type of parametric model for this to draw the data from, and therefore, yes, it is a non-parametric bootstrapping approach. The original estimators were these 3.82 and minus 0.006. The next thing is already the bias, which otherwise we would have had to calculate manually. In this case, it does so for the 1,000 bootstrap samples, and also provides us the standard error, which we also obtained from the original regression summary. So this is the bias of the bootstrap samples. And then there's the jackknife added after the bootstrapping. This jackknife edit is, as I said, a leave one out strategy. So how leaving out one data point affects the whole scenario, and this is what we're looking at here for Bootstrap versions. So by leaving out each of the data points, we obtain different standardized jackknife values, which are for the comparison of how close together the estimates will be just by leaving out a point or leaving it in the data. The more they cluster together, the more they fit together, and leaving out one of them will not have a great effect. The further away a point is in this plot, the harder, the more it affects this estimation. And what we see here is that just having in this point number 13 or leaving it out completely changes all our percentiles of the bootstrap distribution, which we have here. And this is quite the revelation that we already had from this plot and this plot, which is jackknife showing us that leaving it out or taking it in will greatly affect how the regression line is actually going through the points or fitting the points, and therefore this point is a leverage point. The other ones, they are not problematic at all. The reason why exactly these percentiles are chosen, so we're looking at the median of everything, 16 to 84% is working under the assumption that for the normal distribution within plus minus one standard deviation, there would be 68% of all observations, and therefore 16 to 84 is the central 68% of the data. Then there's 10 to 90 percentiles, and of course the 5 to 95 percentiles in order to get these for comparison at the margins. Now let's look at a different way of simulating this data. Unlike before, we now want to do a parametric bootstrap simulation, and therefore we specifically base our new generated data on the model which is simulating residuals, and these residuals are taken from a normal distribution scenarios. This parametric bootstrap scenario is creating us the random number generator. It's specifying that we want the maximum likelihood estimate for all this to be the original value to compare against. And again, we look at these 10,000 samples. What we see here is that the bias for the parametric version is somehow less than the bias we had before, which is what holds true as long as at least the majority of points truly follows the underlying parametric assumption that this is normally distributed data that the y's are coming from with, and that's the problem, one outlier, but simulating from the underlying normal distribution allows us to have some effect of how this line is going, but not having such a large effect of resampling the outlier again and again into our samples. And therefore, this one is less affected by the leverage point than the other estimates we had. Good. So much for bootstrapping. I wish you all the best with doing the exercises, and yes, we will continue then with cross-validation.